Чего? Ну, так.
По-любому да, по-любому наши, типа, тут такое же распределение на столе гнева, по-моему.
Так чего? А если что, ее порежут на кусочки? Если...
ну мы надеемся.
Хорошо. Okay, then let us start.
Да, это опасно.
Okay, let us start. We are going to talk today mostly about Cartier devices. But first of all, maybe I will point out some statements from last time, and maybe I will repeat them if we didn't mention them well. So first of all, I just recall that there is a general statement. If we have a normal variety X, then take any non-zero rational function. So this is a non-zero rational function. It has divisors of zeros and divisors of poles. And we have the divisor of function f is non-negative. It means that it has no poles. It is if and only if f is a morphism from x to c. So it has no poles. It is everywhere defined. And the second is that the divisor of our function is 0 if and only if. So it has no poles and its inverse has no poles. So if and only if f is a non-zero function from x to c star. Do you need an explanation? Or is it okay? Okay. Then I think that we will we will prove first this statement from the last lecture, which we didn't prove yet. It was that there is an exact sequence. I think I stated a little bit more generally that last time. So suppose that we have a toric variety X, which corresponds to fan sigma. Then we have M mapped to T invariant divisors on X sigma. Then they map to the class group. The class group, I recall it as the quotient of all Weyl divisors over all principal divisors. And it maps to 0. In this theorem, if the fan is of full dimension, then it is exact also here. Yes. If the rays span the lattice n, then it will be 0 to m to divisors on X sigma. So it is exact in the left term. I just rewrite the same exact sequence.
What do you mean by Roy?
It means, yes, it is all the rays. in the other words, so it means that the fan sigma is of full dimension. And also, sometimes people say that the variety X has no torus factors. Torus factors is X sigma has no torus factors. It means that if your fan is not of full dimension, then the variety is the product of some small toric variety and a torus of dimension, which is the difference of rank n and the dimension of sigma. If you take a point in n, it corresponds to the torus. So in this case, you can say that it is a direct product of two fans, one in some n prime of smaller dimension, and another is a n of n r power difference rank n minus dimension sigma. And the point in that space is the torus. So if the dimension of sigma is smaller, then x sigma is the product of x prime times torus of dimension n minus some k. This is forbidden in this case. Okay. So torus factors means that if a fan is bad, then x sigma can be quotiented, some torus can be quotiented out. For example, a variety C times C star, it has torus factors. This is a torus factor. This is a torus itself. It means, so it is because the fan sigma is such a ray in R2. So this is not a full dimension. And this is why C stars goes out. And we don't want to, in this theorem, we say that if this is not the case, then the sequence is exact on the left. Okay. What is our proof? Last time we had a theorem how to find the class group. We said that if we have an open subset U such that its complement is a union of divisors, then we had the direct sum of these divisors. We had then it maps to the class group of our variety, and then it maps to the class group of U. In our case, I say that U is the torus which is open in our variety X. And now we know from the end of last lecture that X minus T, in fact, this is known by the orbit correspondence, that X minus T is the union of divisors D rho. So where rho are rays of sigma. This is known. So we rewrite that theorem from last time in the following way. The direct sum of Z D rho, it maps to the class group of our variety X sigma, then to the class group of torus, and then to 0. Okay? This is our U, and this is our X. Now, what is known? In fact, this is the group of Weyl divisors. This is Tn X sigma. This is our class group. now this is the class group of the torus, but we said that since the algebra of regular functions on the torus is factorial, its class group is trivial. So we have 0 here. It maps to 0. Now we can check this. We explained that our sequence is exact here. Now, I didn't mention what are the maps. An element m from here, it maps to the divisor of the character type m. So clearly, if we take the composition here, it will be 0, because a character is a rational function, and if we take m here, then it goes to its divisor, and then it maps to the class group, but it is in fact the principal divisor, so it goes to 0. Okay. What should we prove? What should we prove now? If some element goes to 0 here, why does it come from a monomial? So suppose that
So now we are talking only about Weyl divisors, yeah? And Weyl class group.
yes. By definition, this is using Weyl divisors. If you take Cartier divisors, this is denoted by the Picard group. Yes. So suppose D. What do you prefer? W div or just div?
W div is okay.
Okay. So you take this. You take this D. And suppose that it maps to 0 in the class group. So in this case, since it is a T invariant, we know that its support doesn't intersect with the torus. What do we have? So we have our toric variety X. There are some divisors, and the rest is the torus. So the torus is the open orbit. If a divisor D has a point here, since it is T invariant, it will contain all the torus, and it will not be a divisor. So, so we have a T invariant divisor, and we know that if we take it is D is since it maps to 0, we mentioned here that in this case it is a divisor of a non-vanishing function. So D equals the divisor of some f for some f in Cx star. So this is a non-zero rational function, and its divisor is the divisor of f of D. and the divisor of f restricted to the torus is 0. So it has a 0 divisor as an element of f has a 0 divisor on the torus, and f is a nowhere vanishing function on the torus, and as you checked in the sheet, f is a character. F is in C M star. So f is some constant multiplied by chi m, and it doesn't matter for the divisor. It comes from the divisor of chi m, and we are done. So we took an element from here, which maps to 0 here, and we found m such that the divisor of chi m is the same as our d.
Yeah, but you say that f equal to c chi m.
It is a constant. If we take the divisor of c chi m,
Yeah, it's also equal to.
c is in c is the divisor of chi m. And we are done. Any questions? We checked the first statement of the theorem, that the sequence is exact. This sequence is exact. And now, why is it exact in this term if our fan is a full dimension? Suppose that sigma full dimension, and divisor of chi m is 0. What does it mean? Last time we wrote an exact formula. What is the divisor of the character? We take all the rays, we take primitive vectors on the rays, the divisors is the sum over all the rays rho of d rho taken with the coefficient m multiplied by the primitive vector on this row. Okay? We just said that the order of vanishing of this character along this divisor can be found by the pairing. Okay. But if it is 0, then all the coefficient m u rho will be 0. But since u rho span the whole lattice n, it means that m is 0. And we proved the exactness in this term for a toric variety which has no torus factors. Okay. So the theorem is proven. What else? What else? So corollary for toric varieties, the class group is finitely generated. as we saw last time in the seminar, it can have torsion and it can have contain free subgroups. So any abelian finitely generated subgroup can occur. Okay.
So we didn't know it earlier, that this statement, yeah?
This statement? No, I don't know why.
How we deduce it from this?
But we have M here. Okay.
So it's just a quotient of finitely generated group by finitely generated group, and that means that
Yes.
okay.
Yes. Okay. Now I mention one more theorem which is very similar, and it needs no proof, I suppose. Theorem. Recall that the Picard group is the quotient of all Cartier devices over the principal devices. And so we can write M maps to Cartier devices, T-invariant Cartier devices, then to the Picard group, and to 0. It can be done in the same way. I just need to say that if we take M here and we take the divisor of the character chi M, it will be a Cartier divisor. So all the arrows are well defined and the proof is the same.
But we don't know how, so we know that Veil divisors is all like the sum of Z, D, rho.
Yes.
But do we know how all Cartier divisors do?
Any Cartier divisor is a Veil divisor.
Yeah, that's true, but not any Veil divisor is Cartier.
Not any Veil divisor is Cartier, but we don't need it for this proof.
Right.
What do you want to prove? In any case, you just say that your Cartier divisor is Veil. What do you want to... You just say that any Cartier divisor is Veil. Then you find, for example, this monomial M. But now it gives a Cartier divisor, so the proof works. And in the same way, if it is a full dimension, even if and only if. So the short exact sequence this is the exact if and only if sigma of full dimension. So in one direction we have already explained this, and the other direction is clear. If sigma is not a full dimension, then we can find this M, which will have a 0 divisor, which is not a principal.
Intuitively, how is the map from Veil devices to...
Sorry?
Intuitively, how is the map from Veil devices to Cartier devices?
No. The group of Veil devices is bigger than the group of Cartier devices.
How do we get that from Veil devices to Cartier devices?
We don't have such a map.
But the several here.
At the class group. This is the class group. The quotient of W div over the principal devices. The principal devices, the principal divisors are the divisors of rational functions. I recall that for the projective space, a divisor is a finite sum of points with integer coefficients. And principal divisors are sums of points with zero sum. So both the class group and the Picard group, it is Z because you take the sum of coefficients. Okay. I think I mentioned without proof that if X is smooth, then the groups of Weyl divisors and of Cartier divisors, they coincide. This is a general statement which doesn't need the torus sections. You can prove it using discrete valuations, but I don't want to do it right now. If you want, you can even read it in Cox. This is just a technical exercise. So if it is true for X, then it is also true for T invariant divisors on X. Okay. And now we know something about the class group, but I think that we want to learn more. Do you know something about sheaves? Okay.
The definition.
Only the definition? Okay. Okay. I think that the theory of Toric varieties is the good place to learn about them, because if you believe in some general statements, then you just do something interesting. So what do we need? We need sheaves of OX modules. So X our variety, U is an open subset of X, and so we say that let O X be its let O X be this sheaf. It means that on each U you have a O X U is in fact all the maps from U to C, where phi is regular. So OX is just all the regular functions on our variety X. And on each open subset, we consider those functions which are regular only on U. What else? What else? Now we want to define some other sheaves. Suppose that D is a fixed divisor. Now we define OXD, OXD, which is all the functions. So OXD on U, on an open subset U. It will consist of all rational functions on X such that, in fact, their poles are not worse than d. Formally saying, we write here divisor of this function f plus d, then restricted to u, it should be non-negative. And we add 0 to this set. So, for example, if d is 1 point on P1, we say that after adding this point to the divisor of f, we get a non-negative divisor. So these are all the rational functions with at most one pole at this point given by the divisor. Okay, and what interesting can we say about this? Suppose that we have suppose that if we have a d1 etc. ds distinct prime divisors on a variety x. In this case, I want to say that Ox of minus d is the ideal sheaf of the subvariety of codimension 1 of y, which is the union of these divisors.
D is the sum, right?
Sorry?
D is the sum.
Yes. D is d1 plus etc. plus ds. And then this Ox of minus d is, in fact, these will be all the regular functions on initial variety x, which vanish on this union. They're distinct.
Maybe.
So x is normal, and the divisors are distinct. We don't need to assume this. Okay.
So, and how is this x minus d is defined?
It is defined in this, yes,
Is minus?
yes.
Okay.
So it will get the divisor of is greater or equal than divisor d. Okay. Let us check this. Check locally. So since we work with sheaves, we can check it locally on some open covering, and they then say that it works fine when we pass to the x itself. I don't want to write it in detail, but we say that if x is the spectrum of some r, in this case, if I didn't define, so we say that I want to say that let the global sections on U, gamma U of Ox minus D, okay, no, this is just the global sections of this sheaf. So what do we want to prove? We want to prove that it will be equal to the set f from OXU such that f vanish on Y. This is what we want to prove. And now we check this locally, and we say that if f belongs to the global sections on x over x of minus d, then the divisor of this function minus d is non-zero, so it is greater or equal than d. But now we say that d is defined in this way, so it is effective. Effective means all the coefficients are non-negative. So we write d is non-zero itself. Okay? This is just a notation. D is non-zero if all the coefficients are non-zero. Okay. What else? We know from the lemma in the beginning that if f is non-zero, if the divisor of f is non-zero, then f is a rational function. So f in this case, it belongs to the initial ring. Okay? Just we take a function, its divisor is non-zero, then it has no pose and belongs to R and not to its field of fractions. Okay. So we see that this is an ideal in our ring R. If we sum up two functions of this with this property, or if we multiply them by something, everything will survive. So the global sections of x minus d is an ideal. Now, one technical detail I didn't explain well, but we assume that for each prime ideal, for each prime divisor, its ideal, it is some prime ideal in R. And so we say that if we take f from the ring, the order of vanishing nu di f is positive if and only if f belongs to this prime ideal. Okay? And now we know that divisor of f is greater or equal than d if and only if f is in pi for all I. So f all of pi, so f belongs to the ideal of our variety y. yes, and we are done. Okay. And now one more statement. Is that if we take two linearly equivalent devices, then the corresponding sheaves are isomorphic. I think that we will not need it today, but we will need it later. If D and E are linearly equivalent, this is denoted by tilde. Then OXD and OXE are isomorphic as sheaves of OX modules. So it is not very difficult. We just say that if F belongs to suppose that D is E plus divisor of subfunction G, where G is a non-zero function on X. G is rational and non-zero. Then if F belongs to the global sections of XOXD, it is the same as the divisor of F plus D is non-zero, but we know that divisor of F is divisor of D is divisor D is E plus divisor of G, so this is equivalent divisor of F plus E plus divisor of G is non-zero, but then we can say that the sum of divisors is the divisor of the product. So it means that divisor of FG plus E is non-zero, but G is fixed and F is arbitrary. So in this case, multiplication by G gives this isomorphism. Okay, and we may perform the same for each U in X open. And so we have proved this statement. It explains why do we say only about linearly equivalent devices. Okay, this statement didn't use the toric structure. And now let us pass to the interesting Toric case. We don't know yet how to find the Cartier devices and the Picard group. So let us prove that for each affine toric variety, all the Cartier devices are devices of monomials, and the Picard group is trivial. So, theorem. Suppose that we take a cone which is strictly convex, so it doesn't contain a line. This is the basic our assumption to construct a toric variety. So we construct U sigma on U sigma. First of all, every torus invariant Cartier divisor is the divisor of a character. And second, the Picard group is trivial. Okay. So this theorem is quite hard to prove. Let us start. First of all,
Isn't it something that we discussed, like that the CN for T, we discussed it for T.
yes,
Yeah, that's not.
this is any affine toric variety. Okay.
That's an A for implies B.
Yes. Yes.
That's not so hard.
A implies B. But we need B to be able to say what can be Picard groups of different toric varieties. We will have, if you want, we can start with an example. We can start with, no, a more interesting example. So let us start with an example. So we take the cone of which is given by d minus 1. This is d minus 1 and 0, 1. If we say that this is our sigma, then do we know the class group? I think that yes. We say that the class group of U sigma, we did it last time. It was Z over D. Okay? And also we said that if we prove this, we can say that the Picard group, it will be 0. Now, this is U sigma. Now we can perform something strange. Something strange means that I take only the skeleton of this cone. I throw out one point. Do you remember that this is C2 over this group? Geometrically, this is C2 over this group. So it is not smooth. It is not smooth, and these groups are different. If we throw out the origin, we will get a smooth variety. No cone here. So this is a fan.
Two rows.
Yes, and the origin is for the torus orbit. So this is this C2 over dz without the origin. We had one singular point and we throw it out.
Yeah.
Now we get a smooth variety. It is smooth, it is toric, and it is strange. Since it is smooth, we have that the class group equals the PK group. But what is it? The class group didn't change. Last time we used the formula which uses only the rows, only the arrays. So this is the class group is the class group of U sigma.
So it's contrary.
This is a strange PK group. So the PK group of X is Z over dz. So it has torsion. It is not free, and it is not as in the theorem.
Yeah, but it's not an affine.
Yes, this is just to precise. It is not a trivial statement.
Yeah.
So it is quite easy to make a
Now, first example, Picard group is zero.
if we prove this theorem, if we prove it
By this theorem.
by this theorem, yes. This was an example, just to show that there are varieties, not very difficult, which have torsion in the Picard group. Okay.
Можно вот вопрос?
Да.
Это же был как критерий гладкости. Почему он? Я его забыл.
Ага. Okay.
Почему она не гладкая? Ну, кроме
Кто не
того,
гладкий?
что он группы не совпадает.
Why this variety is not smooth? If it is smooth, then you can locally make it as the product of C and C star. It means that for the primitive edges on the rays of this cone can be completed to a basis of Z power 2 in this case.
But they can't.
They can't be computed. They can't be completed because if you take these two vectors, they give us the sublattice. So either the determinant should be 1, or it should be one ray in two-dimensional space, and then you can complete it to a basis of Z2. So in each affine chart, so each affine U sigma is smooth if and only if the primitive vectors on the rays of sigma can be completed to a basis of the corresponding lattice. There was one cone which doesn't satisfy, and we throw it out. And this is glued up of two copies of two instances of C times C star. For each ray, this is C times C star. Okay. Now let us prove this theorem. We denote R as C sigma check intersected with M to be as the, so this is the algebra of regular functions on U sigma. And now first case, case 1, we have a T-invariant Cartier divisor. So D is our divisor. so each Cartier divisor is a Weyl divisor, and we know that each T invariant Weyl divisor is supported on our D row. And so each D can be written as a sum of some G row with some coefficients. First case, so D equals the sum of A row, D row. D is effective, so which by definition means that all the coefficients A row are non-negative. First of all, we take this divisor and we want to find a character such that its divisor is D. So we write that the global sections of U sigma and O U sigma of minus D is an ideal. Should I write it precisely? This is all the functions f from R such that either f is a zero function or f is non-zero and its divisor is greater than D, is not less than D. This is an ideal of this subvariety I in our functions R. Okay? Then, since our divisor is T invariant, this ideal is also T invariant. So since D, oh sorry, okay. Now what else? We know that if an ideal is T invariant, then it is a direct sum of characters. Each T invariant function is can be decomposed as a sum of characters. Do you recall this? We proved it in this sheet, I think. It is the direct sum of some characters which all belong to this ideal C chi m. So if a function is T invariant, it is a sum of characters. And each character itself, it belongs to this ideal. So each m satisfies the inequality. The direct sum, we need that the divisor of chi m is greater or equal than D C chi m. Okay? Maybe I erased the example. Okay, but this is not the end. Now we want to find, in some sense, the smallest m, which will give us the same divisor as D. And we need some more work. So we have several arrays. And we know that O sigma, it is the torus orbit corresponding to sigma. It belongs to the intersection of all divisors. If sigma is of full dimension, this is one point. And if the dimension of sigma is smaller than these some torus of some dimension. So now we fix a point P in O sigma.
Intersection of
All, yes, this is all.
What?
I can explain. We know what is the closure of a torus orbit.
Yes.
And so, if we take O rho, and if we take its closure, it contains all the orbits such that rho is a face of that. Yes, since rho is a one-dimensional face of sigma, then O rho bar, it contains O sigma. But by definition, O rho bar is a one-dimensional subvariety which we denote by d rho.
Yes, so it means it should be intersection by all rays of sigma.
Yes, so we have the smallest torus orbit O sigma. For each ray, it belongs. So for each rho, we know that O sigma is a subset of D rho. Is it okay? For each rho, O sigma is in D rho.
That we in a fine case. Yeah, because of we.
Yes,
fine
yes,
case,
we're in
that
the fine case. Yes,
trivial.
yes, yes, we're in the fine case. So if we take the intersection of all the divisors, it is a non-empty set. It contains at least one point. Exactly one if sigma is of full dimension. So it is, in some sense, the worst point of our divisor. It is the worst point, but our divisor was Cartier, and so even at this point, it is a divisor of some rational function. So
So when we say strictly convex, we mean that there is only one point.
if we say strictly convex, it means that it doesn't contain lines.
So it can.
The dual can contain lines, but the cone itself not. So we fixed this point. Since D is Cartier, it is locally principal. So there exists some neighborhood of our point P such that some neighborhood U of P such that D restricted to U is principal. But now I want this U to be a principal open subset. So without loss of generality, we may shrink U and say that U be U sigma H for some function H in our regular functions, such that in the point P it is non-zero. Okay, this is the principal open subset. Okay. Now one more. We know that D restricted to U, it is the same as F restricted to U. F is this function such that its divisor on U is the same. F is taken from R star. So it is a non-zero, no, it is in C U sigma star. It is a rational function on our U sigma.
Why is such a
We say that D is locally principal. So in some neighborhood of P, it is principal. Let it be defined by F. But now we know that D is effective. So F is also effective. So F is in the localization RH. Okay? Since it is defined here and is non-zero. But now I want to change F. I know that the divisor of H restricted to U sigma H is zero by definition, because it was a rational function and we throw out its zeros. And so without loss of generality, F is in R. Otherwise, multiply by H power something. Okay? What do we have now? Now we assume this. What else? We know what is the divisor of F on this open subset, but we don't know what is the divisor of F. We can write the divisor of F. It will be the sum of for all the rays d row with coefficients as the valuations d row F plus something plus some other divisors but also we know that F is in the regular functions, so its divisor is non-negative. It has no poles, so no summands with the minus sum. So this is non-negative, and now we can write that this is greater or equal than this sum.
What is here?
These are some components which are not toric. So we found some function. We don't know that it is T invariant.
Yeah, that's true.
So it's greater or equal than the sum for all the raise nu d rho f d rho. Okay, and this is exactly d. We started with the divisor d, and this is exactly that divisor. Just by definition. We took a torus invariant divisor.
Yeah, but new dr of f, why is it ar? Very well.
Because I explain. So on u we have the equality.
Yeah.
What is our u? This is the point which contains the point where all the divisors pass.
Yeah.
So this subset has a non-trivial intersection with all the divisors. There are no divisors which are forgotten. So if we write down d, it is decomposed at this sum with some coefficients. But the coefficients are the same because we assume this. And all the d rho participate in this equality. Okay. So now we know that since for f we have all these inequalities, then f is in the ideal of global sections, and it can be represented as a sum of characters. So now we obtain that f is in this ideal. Now, since it is in this ideal, now we can write down that f is a sum of some monomials. Is the sum of ai chi mi. We use this presentation. We want to find a monomial which is non-zero on u, and this will be what we want. We know that all div chi mi are greater or equal than d. Okay. Now, if we write down the quotient, we obtain that if we take a quotient, this sum, if we divide it by f, then on u, we know that the divisor of chi mi is greater or equal than d is the divisor of f. Okay, so this quotient is well defined on u.
Why is this equality false?
F is in the ideal. We know the description of this ideal. All the monomials satisfy this inequality. On the other hand, we know what is the divisor of f. Divisor of f on u is the divisor of d on u, which is the divisor of d. Okay. Mm-hmm. So it is well defined on U, but on the other hand, this is 1 on U. And we know that U contains point P. Look at P. There exists some I such that one of the summands will be non-zero. That chi mi over f at P will be non-zero. So we have a sum which equals 1. If all the summands are 0, then it will not be 1. So there exists some v in U such that chi mi divided over f is non-vanishing on this subset V. Okay? Such that P belongs to V. Okay?
I don't understand still why here mi divided by f is non-defined.
Yes, we had a statement that if a rational function has a non-negative divisor, if some function which is it is a rational function, not identically 0, such that divisor of f is non-negative, it means it has no poles, then f is in fact rational. We use this.
Yes. Okay, then I don't understand why divisor of e to the power of I is...
Because when restricted to U, the divisor D is principal, it is the divisor of F. So the divisor of U over F is by definition D. We just chose F in such a way.
Yeah, they coincide on U.
Yes, they coincide on U. We work on U in that part. They coincide on U. The inequalities hold. So if we take the difference, it will be non-negative and it will correspond to a regular on U function. Okay. So we have a non-vanishing function on V. So the divisor of this character, when restricted to V, will be the divisor of F when restricted to V, and it will be D restricted to V. Okay, and we know that both these divisors have support is contained in the union of D row, and V intersects all D row since it contains P. So its intersection with D row is some open subset of D row. And if these restrictions are equal, then the divisors are equal, because they both have these summands and the coefficients will be the same. So globally, we have that the divisor of chi mi is the divisor D. Okay. And this is the proof of part A. Now, no, this is not the proof of part A. We assume that D is effective.
Yeah, that's true. That's proof of case 1.
This is case 1. So what about case 2? It is not very difficult. Case 2. D not.
Please repeat the last step.
Yes. The last step.
So I agree that all the three divisors of the V are equal.
Yes. What is the support of a divisor? This is
Yes, they are.
the union of its non-trivial components. The character is a function which is non-vanishing on the torus. So the divisor of the character can contain only the components only equal to d rho. Then D. It contains only the components d rho because this is where we took d rho from.
Yes.
Maybe it is not all the rows, or not all the rays. What about V? V is a very interesting subset of our U sigma. So, where is our point P? Our point P. Point P in O sigma. It means that, so these are divisors, and point P is here. And the open subset contains P. This is our V. It contains P. So if we restrict all the divisors to P, these components will not disappear. Maybe some rays of our fan disappear. Maybe some elements which are here disappear. But it doesn't matter. No, they will not disappear because this character, its divisor is greater or equal than D. So if it contains more components, one moment. But this is non-vanishing on V. If it will contain another component, then the quotient will vanish on V. So it cannot contain other components. Is it okay?
So we say that divisor of key to the power mi and d coincide of d.
Mm-hmm.
They will support from this divi.
Yes.
Then we want to claim that there are no other components.
Yes. Yes.
Okay, it's more or less clear.
Mm-hmm. Okay, so the statement is proved if we assume that D is effective. Okay? And now the easy case, when D is not effective, then we know that dimension of sigma check is the dimension of MR. And then there is a point in its relative interior, so there exists M such that M U rho is positive for all rho in the rays of sigma. Okay? This is just any point from the relative interior is okay. In the relative interior of sigma check.
Dimension of sigma check is equal to dimension.
Yes. If sigma doesn't contain lines,
Yeah, that's true.
then sigma check is a 4-dimension. Okay. So in this case, the divisor of the character chi m contains all the row with contains all the row b row d row such that all b row are positive, and then we take d plus some big k divisor of chi m such that it will be positive. There is this k, an integer k, such that it will be positive. Just if some coefficient is negative, we sum up it with b row many times to make it positive. Just there is a monomial such that its divisor contains all the rays. And we sum up with it many times to correct all the coefficients. Now when all the coefficients are positive, then we can apply this. Oh, I see. If you write strictly positive here, then it will be perfect. In this assumption, we may assume that all the coefficients are strictly positive.
Why is it matters?
If you want to explain that no summands disappear here,
Yeah, but they can't disappear. That on V they can't disappear.
on V, if we write that all the AI are strictly positive, then they all appear on V.
Yes,
Yeah.
but
Try that they still appear on.
yes, this is
Yeah.
What's problem?
Okay. Okay, I think it will be better when a row is strictly positive. So when we sum up with this chi m, we can always obtain that they will be all strictly positive. And so if the divisor of d plus the divisor of some character will be the divisor of the character, then the divisor of d is also the divisor of some another character. Okay, and the part B is obvious, so we are done. Okay. Maybe I prove something else. Is it okay? Maybe I prove one more statement, and then we will end the today lecture. Okay, I want to prove that if the fan contains a cone of full dimension, then the Picard group is free. What should I erase? I erased the theorem. So, another theorem. Suppose that X sigma be a toric variety with the fan sigma. So, if sigma contains a cone of dimension n, then the Picard group is free. So recall that we had an example with such a strange fan. It had no cone of dimension 2. And its Picard group was Z over dz. And if we assume that there is a cone of dimension n, we avoid this situation. So how do we prove this? We had an exact sequence. Where M maps to the Cartier devices, and then to the class group. So M maps to Cartier devices, then the Picard, and then to 0. So if we assume that the Picard group has a torsion, then it means that there is a T invariant T n.
Should be C diff invariant.
Sorry?
It should be C diff T invariant, right?
Yes, T invariant. Thank you. There exists a T invariant device D Cartier. And such that sum its multiple KD has so if we take an element which is the torsion, we say that KD is the divisor of some character. And we here have K is positive. Okay?
So the D is both T invariant and Cartier.
D is T invariant and Cartier, such that it maps to the element which has torsion in the Picard group. If it maps to the torsion in the Picard group, then its multiple for some positive integer k maps to 0. So we know the exactness here. So if KD maps to 0, then it comes from some monomial. Okay. So KD is yeah. Now let us suppose that the cone sigma has dimension n as full dimension in our fan. Then we restrict to use sigma. In this case, we restrict a Cartier divisor and we get a Cartier divisor. So we know that D restricted to, we assume that KD is the divisor of chi m, where m is taken from m. So D restricted to U sigma is, it contains only those rays which appear in sigma, and it is the sum of A rho D rho, where rho are taken from the sigma of 1. Because if we have such a picture, for example, this is sigma and this is rho. In this case, this divisor doesn't intersect, so its intersection with U sigma is only 1 point. It doesn't belong to U sigma. Okay, we write down D restricted to U sigma, and on the other hand, we know that on U sigma the Picard group is trivial, so there exists some m prime in M such that D restricted to U sigma is the divisor of chi m prime. Okay? But now if we look here, maybe I multiply something by D. So the divisor of M minus D in prime, what is the divisor of chi M minus D in M prime restricted to U sigma? It is KD minus KD. No, there are the K small, no D small. I wanted to say K here, thank you. This is K, which is used here in the torsion. The K is taken from here. So the divisor of chi m minus k m prime, it is the divisor, its divisor is KD from here minus, we know that D on U sigma is chi m prime on U prime. This is 0. On the other hand, for the character, we know how to expand it. For the character, we know that the divisor of chi m minus chi m prime on U sigma. This is the sum of sigma of 1. This value is the product of the monomial with U rho. M minus k m prime U rho D rho. Since it is 0, then all the pairings m minus k m prime U rho are 0. Since we have enough U rho, So if sigma is of full dimension, then use sigma from a linearly independent space of full rank, and m minus k m prime is 0. And d, the initial divisor, is the divisor over chi m prime. And we are done. So it is principal, and it is 0 in the Picard group. So there is no torsion in the Picard group. The Picard group so we are done. Any questions?
Is it true that the subgroup of finitely generated group is finitely generated
A subgroup?
of abelian? So I want to say that Picard group is finitely generated.
No, it is not true.
Not true. Okay, but then we prove that there is no torsion, but maybe it's still true.
Everything is subgroup of
Oh, sorry.
Is it true that if some abelian group has no torsion, that it is free?
Yes, it is true.
It is
It
clear
is.
to finitely generated group.
But in our case, it is finitely generated. Because we know that we have only finitely many divisors.
Yes, but then the Picard group is finitely generated.
Yes, but in general, your statement about finitely generated groups, I need to think about it. Yes. Okay, any other questions? Okay, then we will end here. А кто может трансляцию остановить?
Что?
Трансляцию можете, пожалуйста, остановить?
Вообще не представляю.
Да?
На кнопку можно нажать.
На кнопку.
Раз работает.
На кнопку. Сейчас. Давайте.
Seminar, so I need to go.
One moment.